1. How Antonys little animals led to the development of germ theory. In today's era of the electron microscope, the Hubble telescope, and satellite transmission of images from the surface of Mars, the observations of an unschooled shopkeeper in Delft in the 1670s of a hitherto unknown world prove even more astounding. Antony van Leeuwenhoek, pronounced Ley van Hoek, earned his living as a draper, but surely ranks among the greatest self-taught geniuses in the history of science and medicine. Having become skilled in grinding and polishing lenses to inspect cloth fibers during a youthful apprenticeship in Amsterdam, this amateur scientist of limited education designed and built simple microscopes with astonishingly high magnification and resolution. With these, he first observed microorganisms. Leeuwenhoek not only used his lenses to more closely inspect small structures that the naked eye could discern, duck feathers, seeds, mold, the parts of a bee, but he also had the curiosity to move beyond the understanding held by more learned contemporaries and peer into what had been an invisible world. Leeuwenhoek lived during the much-heralded age of exploration, which introduced to Europe, among many other products, spices from far-flung continents. Leeuwenhoek wanted to find out, by the microscopic examination of macerated peppercorns, why pepper is hot. He thought the peppercorns might have spikes on their surface. Examining a suspension in water, he was surprised to see what he called very little animalcules, which were without question bacteria. His observations were detailed over the next 50 years in 375 letters, frequently illustrated, to the Royal Society of London for Improving Natural Knowledge and published in its Philosophical Transactions. It was his famous Letter 18, dated October 9th, 1676, that caused a sensation and earned him immortality for his discovery of protozoa and bacteria. His descriptions allow us to share his wonder at the microscopic appearance of a new world of little creatures in rainwater that had been left in a barrel for several days, well water and seawater. He saw that what modern science knows as protozoa, first animals, used tiny legs or tails to swim in the tiny drop of water that was their world. We can share his sense of awe as he observed that the motion of most of these animalcules in the water was so swift and so various upwards, downwards, and roundabout that 'twas wonderful to see. He observed protozoa entangled in a filament expand and contract their shape, struggle by strongly stretching themselves to extricate themselves, and he marveled when an animalcule brought on a dry place burst asunder. Observing no skeletal parts or obvious skin in an animal whose body consisted of soft protoplasm was a considerable novelty at this date. These observations would not be followed up until Letter 39, dated September 17, 1683, when he examined the plaque from his own teeth and was stunned at the number of bacteria he found. He estimated that there are more animals living in the scum on the teeth in a man's mouth than there are men in a whole kingdom. From this microscopic menagerie, he clearly described and illustrated all the morphological types known today: round, cocci, rod-shaped bacilli, and spiral-shaped spirochetes. Leeuwenhoek came tantalizingly close to grasping the germ theory of disease when he found animalcules swarming in the decaying roots of one of his teeth and in the plaque from his own and other people's mouths. He noted that people who cleaned their mouths regularly had much less plaque than those who did not, and coming within hailing distance of heat pasteurization, he saw that the animalcules in plaque could not endure the heat of my coffee. It took 200 years from Leeuwenhoek's first observations until the germ theory of disease and the first effective germ-fighting treatments were established. The delay was in large part due to the fact that all biological processes are chemically based and mediated, and thus progress in medicine was intertwined with progress in chemistry. Frenchman Louis Pasteur discovered the role of bacteria in the causation of disease. A chemist and not a physician, Pasteur was working on problems besetting burgeoning French industries. They quickly led him from chemistry to reveal the workings of biology. Looking at wine under a microscope, he unraveled the fermentation roles played by living yeast organisms and bacteria in the delicate balance between wine and vinegar. But Pasteur wondered, if these organic changes were caused by tiny living microbes, where did they come from? Were they in the air, waiting for favorable conditions to multiply, or were they generated spontaneously by the lifeless matter itself? By 1864, in a series of ingenious experiments, he proved that living organisms do not spontaneously arise, but are present in any material because they are introduced, then reproduce. He showed that the air is never free from living organisms. The first disease Pasteur attributed to a living organism was one that was devastating the silkworm industry. By 1870, he showed that it was due to a protozoan infesting the grain the silkworms were fed. Pasteur was elected to the Académie de Médecine in 1873. On February 19, 1878, before the Academy, he presented his germ theory of infection. He laid out his conviction regarding the causal relationship between microorganisms and disease, that specific organisms produce specific conditions, that destroying these microorganisms halts transmission of communicable diseases, and that vaccines might be prepared for prevention. A revolutionary dictum now illuminated the way toward productive research, practice, and therapeutics. However, this was not universally greeted with acclaim. Some doctors called it microbial madness and disdainfully asked Pasteur, "Monsieur, where is your MD? Are your hands clean?" Meanwhile, an English surgeon named Joseph Lister, inspired by Pasteur's work, inaugurated the era of modern surgery. In 1865, he began a program to prevent sepsis by using carbolic acid as a disinfectant, markedly reducing the incidence of postoperative infections. As the remonstrations of Ignaz Semmelweis in the late 1840s and 1850s against the unwashed hands of obstetricians received the scorn of his colleagues, so did Lister's technique meet the rigid objections of the surgical establishment before it was generally accepted 2 decades later. Another advance in reducing surgical infections was serendipitously introduced by William Stewart Halsted, professor of surgery at the Johns Hopkins University Hospital and Medical School in Baltimore. Halsted's OR nurse, Caroline Hampton, whom he would later marry, suffered dermatitis of her hands from repeated exposure to the sterilizing solution, mercuric chloride. In 1891, Halsted asked the Goodyear Company to make thin rubber gloves, which he then had her use to protect her hands. Before long, it became clear that the wearing of gloves, and later surgical gowns and masks, and the heat sterilization of instruments by operating room staff prevented infection in surgical patients. Pasteur himself took the next giant step as he turned his attention to a disease destructive to French poultry farms, chicken cholera. An unplanned discovery provided the first useful model for the preparation of a vaccine. Pasteur knew the value of cultivating a mind receptive to surprising occurrences. In his inaugural address at the age of 32 as professor and dean of the new Faculty of Sciences in Lille in 1854, he proclaimed a maxim that resonates to this day: where observation is concerned, chance favors only the prepared mind. Repeatedly, his own activities proved to be striking illustrations of his statement. If healthy chickens were injected with a culture of cholera microbes, they invariably died within 24 hours. But one day, in 1879, upon returning from a 3-month-long summer vacation, he tried to restart his experiments using a culture he had prepared before leaving. He was surprised to discover that nothing happened. The injected chickens remained quite healthy and lively. With the genius for exploiting what looked like an experiment gone wrong, he followed with the next logical step. Injections of fresh, virulent cultures into the same hens now failed to produce the disease. Pasteur immediately recognized the significance of what he had blundered into. He had found a way of attenuating the cholera microorganisms artificially. He had succeeded in immunizing the chickens with the weak, old bacterial culture. A new truth was discovered. Attenuated microbes make a good vaccine by imparting immunity without actually producing the disease. Vaccines could now be produced in the laboratory. 2 years later, Pasteur produced a vaccine against anthrax, a highly contagious disease that was killing large numbers of cattle in Europe. It was also known as wool sorter's disease because people contracted it from their sheep. In 1885, Pasteur had a triumphant success with the introduction of a vaccine against the terrifying disease rabies. 3 years later, the Pasteur Institute was established in Paris, becoming, in time, one of the most prestigious biological research institutions in the world.